Okay, today's video, we're just going to cover the start of the next statistics chapter which we need to do, which is based on a normal distribution. It's quite a long chapter, so we're going to break it up into a few little sections. So today it's just going to be on the basics, what it is, what it looks like, and possibly the inverse as well. And then we'll leave it at that. Okay, so just to start off with, I think it's really important just to sort of rewind slightly and consider what we already know about the binomial distribution, which we've recently covered. And how it sort of compares and contrasts with the normal distribution. Okay, so that's what we're going to do to start off with. I'm just going to flip the camera around so we can have a little look at what I've written down. Okay, so just very quickly then, for the binomial distribution, we know that we write it x, or whatever letter you want to use for your variable. It's distributed binomially NP, where n is the number of trials, and P is the probability of success, inverted commas, for that trial. We know there are certain conditions for the binomial distribution, such as, a fixed number of trials, only two options, constant probability of success. So we kind of know how it works. And the key word which we need to link with the binomial distribution is discrete. Okay, it's for discrete data, discrete variables. So, for example, if we had a random binomial distribution, 10 trials, probability of success 0.5, so maybe it's flipping a coin 10 times, we know that we can get, using the BPD function on our calculator, a value for the probability of there being two heads, let's say, and that could be 0.043. We also know, because it's discrete, that if we receive a question such as this, px is less than 5, we do need to convert that into px is less than or equal to 4. Okay, that's a discrete aspect which we're seeing there. And again, we know that we can get a value for that. Okay, so this is how the binomial distribution is going to be working, but the key word we need to link to that is discrete. Now, moving on to the normal distribution, similarly to binomial, we're going to write our distribution. Okay, it's really, really important. And again, we need, if it was to be in a sort of real context, we'd say let x be the something or other, but x is distributed normally, and we're going to use mu and sigma squared. Now, we've seen these two letters before. Mu represents the mean, and sigma squared is actually the variance, but we could see this as a standard deviation squared. Okay, and we're going to sort of talk about that in a little bit more detail later on. Now, key thing for normal distribution, which is a little bit different to binomial distribution, is that I really think it is important that we draw and visualize the normal distribution on a regular basis for almost every question. Okay, and the reason is because actually the normal distribution is really, really easy for us to draw. Okay, the normal distribution is a nice bell-shaped curve. Okay, it's symmetrical, and importantly, if we just consider mu sigma squared, it's symmetrical about its mean. Okay, now just sort of looking at this, it's nice and sort of clear picture. All normal distributions, can I just emphasize this, are the same shape. Okay, this bell-shaped curve. Now, I've written down three normal distributions here, 55 squared, 52 squared, and 50 0.5 squared. So you'll notice that they all have the same mean. So in this example, all three of these curves are going to be symmetrical about 50. Okay, it's actually a value. That's our mean. Now, I just wanted to show you what the standard deviation or variance sort of is about, okay, and what changes maybe. A reminder that standard deviation is the average distance away from the mean. Okay, so we've got an understanding of what that is. So the red distribution, let's say that is what this is, okay, 55 squared. Now, if we consider the blue distribution, like I said, will be exactly the same curve, okay, but what we'll see is actually that it will go in a little bit further before we see our curve, okay? Because what we're saying is this distribution has an average distance away from the mean, which is smaller than this one, okay? So the data is less spread out, okay? That's what you can see here. And were we just to take that one step further, x distributed normally 50 0.5 squared, we'd see exactly the same, but to an even greater extent, looking a little bit like this, okay? So our normal distributions are all going to be the same shape. They're all going to be bell-shaped curves. They're all going to be symmetrical about the mean, and actually the median and the mode as well. That's all one value for normal distributions. But the key thing is that we understand the rough shape of that. Now, just before we move on, I do just want to talk about one thing. Bear with me with the camera just for 1 second. In terms of sort of considering the normal distribution without a calculator, it is actually possible. Generally, we're going to use a calculator, and we obviously know that we've got a calculator in any exams which we are to do. But I think it is actually quite nice just to talk about one very quick rule which we can use. Now, I'm just going to draw a nice normal distribution again and flip you back round. So let's just say we've got this normal distribution. The first thing which we just want to sort of talk about is that here, okay, This is a point of inflection where it goes from concave to convex. That happens at mu plus sigma and at mu minus sigma. Okay, so we're going to have a point of inflection, one standard deviation above and below our mean value. Okay, now actually, the reason we want to visualize a normal distribution so much is because we are going to consider the area underneath this curve to be our probability. Okay, area equals probability. And actually, we can say that the area, therefore, underneath this curve is equal to 100% or 1. And we're going to talk about that in a little bit more detail in 1 second. But using this mu plus sigma, mu minus sigma, what we can actually say is that there is 68% of our data, or probability of 0.68, within that range. Okay, one standard deviation above and below, that's 68%. Now, were we to stretch that slightly further, so mu plus or minus 2 sigma, and mu plus or minus, sorry, that should be minus now, 2 sigma, what we'd say now, between these two, is that we have captured 95% of our data. If we go one more standard deviation, so 3 above and 3 below, we've actually got 99.7. So we've got a nice visual, and we now understand how maybe we can use just the numbers which we get. Remember, mean and sigma, we can do this possibly without calculator to get these specific probabilities, 68, 95, 99.7. Now, it's taken as read that 5 standard deviations above and below the mean is everything. Okay, that's 100%. In reality, I think it's 1 in 1.7 million values or something will fall outside 5 standard deviations above and below. So we can say with a good degree of certainty that everything lies within 5 standard deviations above and below. Okay, but symmetrical about the mean, and we can use these values just to consider some basic probabilities, 68, 95, 99.7. So let's move on slightly, and let's just consider again the difference between this and the binomial. Whereas the binomial is discrete, the key thing here for normal distribution is that it is going to be continuous. So, just wanted to show you one very quick little trap, which we just need to be aware of. X is distributed normally 18, 10 squared. Now, we know, don't we, that sigma squared is how we write the variance. And so what we've got here is the mean, 18, and the variance is 10. Now, we can also write this distribution. It's the same thing, this distribution, as this, 18 and the standard deviation squared. Okay, so we can write our normal distribution one of 2 ways. We just need to be really careful. Is it the variance or is it the standard deviation? Okay, because we're going to plug in the standard deviation to our calculator when we actually use this. Okay, so just be a little bit careful, but those 2 things are the same. Now, when we said for the binomial, if we had like px equals 3 or something, we could get a value for that. The key thing which we just need to understand now is because this is continuous, it can take any value in a range. If we consider this distribution, 18, 10, the probability of x equaling 16 is 0, okay? It is so infinitesimally small that we are going to say it is 0. There is 0 probability that is going to actually equal 16 dead. Okay, it might be 16.001, 002, 003, whatever it might be, okay? But the probability of it actually being 16 dead is 0, okay? It is impossible to get a value for a probability of something equaling a certain value, okay? That's a facet of a continuous distribution. So, if we considered something which is maybe a little bit more continuous, we're going to use the NCD function on the calculator. I'm going to show you how to do that. We can consider same distribution, probability x is less than 16. Now, again, I just want to reiterate, I really think we should be trying to draw this. So if we had this distribution, it doesn't matter how steep the curve is. That was just the point I was making earlier. The key thing is it's symmetrical about 18 and it's a bell-shaped curve. If we've got x is less than 16, firstly, we know just numerically 16 is to the left of 18, and so we're looking for this. Now, if we know that the probability under the curve is 100% or 1, clearly this answer, which we're going to get, is going to be less than 0.5, because it's less than half our bell curve. But what we're going to do is we're going to get our calculator. We're going to go to our statistics mode, and we're going to go to distribution, normal, NCD, and we're going to put in upper 16, lower 0, our mu is 18, and a reminder, if we had our variance as 10, our standard deviation is root 10, and guys, you just type in root 10 here, and it will convert it to a decimal for you. And we can get a value there for p equals 0.2635 to 40p, and give your answer relatively long. Now, just to add this once more, that means, therefore, doesn't it, if px equals 16 is 0, that this is actually equal to px is less than or equal to 16. Okay, so whereas for the binomial we had to fiddle around with, like x is less than 5, we had to convert it to x is less than or equal to 4, we don't have to worry about that for normal distribution. Okay, if we get either of these questions, we just launch into the question straight away with our upper boundary as 16 and our lower boundary as 0. So that's how the continuous distribution works in its sort of normal phase. What I think we'll just finish off with is just a quick look at working the other way. It's called the inverse distribution. And so if we consider another distribution, here's this trick again. This is the variance, isn't it? So we're going to have to say that's root 12 squared on our calculator. But if we consider x is distributed normally 20, 12, the probability that x is less than a is 0.4. We're given that information. We're trying to find now the numerical value for a as opposed to the probability. So we're working backwards. Now again, just thinking about the bell-shaped curve and understanding the symmetry, because it's only 0.4 and it's a less than question, we know that a has to be less than 20 because it's less than 0.5 again, isn't it? So what we're going to do is we're going to go to our calculator. We're going to go distribution, normal, and there's an inverse normal distribution. Now, the key thing, the area, as I said earlier, is the same as probability, so I'm going to put 0.4 there. We need to put in our new mu, which is 20, and I think we said that our sigma was going to be root of 12, which it will convert to a decimal. Now, the information here, the tail, that's quite important. The tail is to do with which end of our distribution we're at, okay? And so clearly here we're at our left-hand tail, because we are less than, okay, but do just consider sort of right-hand tail as well. But we can get a value there for A, which is 19.12, okay? And just to double check that fits, just make sure you're using a bit of common sense here. Is that less than 20? Yes, it absolutely is, so we're going to be fine. Okay, so just a very, very quick video sort of introducing the basics of a normal distribution. Hopefully that makes a little bit of sense, and I'll make another video shortly covering stuff like the standard distribution and beginning to look at some hypothesis tests as well. Okay, thank you.